Now suppose our parameterized curve bounds a region above the x-axis, and we want to find the area of that region with a definite start point and a definite end point according to the x values. In particular, we don't want our curve to intersect with itself, loop back onto itself. We can use parameterized equations to be able to calculate the area of this region by starting with how we calculate the integral formula. So y is a function of x, and we take the integral with respect to x from the start x value to the end x value. And we use the idea that our x is really just a function of t, and our y is really, our x is just a function of t, and our y is really just a function of t. And maybe we can use a u-substitution here. To figure out what we should substitute in for the differential dx, we should take the derivative of both sides of this equation. So dx equals f prime of t times the differential of t. We then just substitute things in here, where our t really begins from little a and ends at little b. Our function y is really the g of t, and our differential dx is really the same thing as f prime of t times dt. With this formula, we can go ahead and calculate the area of nice enough regions bounded by parameterized curves. Let's take a look at this example over here, where our x is defined by this function, our y is defined by this function, and we're trying to find the area of the region cut off within the first quadrant. The first step is to graph the region. In order to save time, it's fair to plug these functions into, say, something like GeoGebra and have it graph the curve for you. One way for GeoGebra to understand you want to graph a parameterized function is to use the parentheses notation to specify points in a plane. My x-coordinate is the f of t. I put a comma, and then I write in my y-coordinate, which is the g of t. It correctly interprets that I wanted to calculate. And looking at this graph, I can see that my curve intersects the y-axis and the x-axis. The trick is to figure out what time parameter gives me the y-axis intercept and the x-axis intercept. I find those in my paper by saying, well, the y-axis intercept means the x-coordinate equals 0. So I have my x-coordinate function, and I want to know what time makes it equal to 0. So I solve this equation over here to say that my y-intercept, or my x-coordinate, is equal to 0. It happens at time t equals 0. Now I want to find my x-intercept, and that means my y-coordinate is equal to 0. So I set my y-coordinate equation equal to 0, and I solve. So I have my second point, my second time parameter that gets me to the x-intercept is equal to the natural log of 3. This gives me my limits of the integral. I have to take the derivative so I can find the differential for my dx. Then I do my substitution according to the formula. We can evaluate these integrals, which gives us the following area. We had to use integration by parts for this particular integral.